Okay. So we are now getting into something called as SVM. Though SVM is not extensively used in the current world, once it was considered to be the best algorithm, like we have deep learning algorithms now, SVM has ruled the world in the past, similar to what we have, similar to neural networks that we have for now. Okay. The main idea of SVM is to create a boundary which is going to divide the two classes or multiple classes. And SVMs can be used both for classification purpose as well as numeric prediction. If you have a number, it can be used for that purpose also. It can be used to solve prediction problems, and it is also used to solve classification problems. When it comes to classification, it can handle two-class classification problem. And when you have multiple classes, how to take it forward is something that we will understand. Okay. So if you have these two classes, circles and squares, you segregate these two classes using a line. This is called as a classifier. This is something that you are able to see when it comes to 2 dimensions. When you have 3 dimensions, x1, x2, and x3, and if you have these data points hanging, assume that these 3 are 3 corners of the room. Like you have x2, say x1, and x3. You're seated in a room, right? Think about the height until your ceiling as one axis. Then in the room, imagine this is one wall. Imagine this as another wall. Then all these data points assume are hanging from the roof. If you take this glass and if you insert the glass like that in the space, if you insert, all the points which fall above would belong to circle. All the points below would belong to a square class. And this is called as a hyperplane. This glass is called as a hyperplane, which segregates these two classes. Suppose you have these two classes, circles and square. You can have multiple hyperplanes which can segregate these two classes. But we are interested in segregating the classes in such a way that the misclassification is minimum. The error is minimum. Okay, that is how we want to classify. If we have A as a classifier, then a circle which falls here would be misclassified as a square, because anything which falls below this dotted line would be a square. So this point would be misclassified. Though it is a circle, it will be classified as a square. And if you have a data point here, say it is a square. Since it's falling above this dotted line A, it will be classified as circle. That would be a misclassification. And then if you see, if you observe C, that also will have certain misclassifications. For example, any data point on the right side will belong to a circle. Any data point which falls towards the left side will be a square. Okay. And you have this dotted line. Here, if you have a data point here, since it's falling towards the right of this classifier, C, it would be misclassified. This circle will be misclassified as a square. Okay. Also, if you have a square here, this would be misclassified as a circle because it is falling towards the right of this. So misclassifications are possible. Now look at B, which is another classifier. According to B, the data points which fall on the right side would be classified as circles. So this and this are circles, and they'll be correctly classified as circles only. And if you look at the right side of this B or below B, these 2 points, which are actually squares, will be classified as squares only. So there is no misclassification here. The moment you have B, misclassifications are not there. But if you look at A or C, there will be misclassifications. So we need to come up with a classifier which gives you minimum misclassifications. Okay. To come up with a classifier which has the least misclassifications, you need to ensure that it has the maximum distance from the data points which are on either side. This line should have the maximum distance. If you look at A, it is almost touching, right? This A is almost touching that. C is also almost touching there, right? But B has a maximum distance. If you have the maximum distance, that means you're giving maximum margin for error, for maximum margin to ensure that errors do not occur. So what you do is you just join all the outermost data points, and we call it as a convex hull. And you join all the outermost data points, and you call this as what? Convex hull. And you want a classifier in such a way that it has a maximum distance from the data points towards the right and towards the left. And if you take this line and if you move it towards the increasing side, the data points which this classifier exactly touches would be called as support vectors. They are supporting this line. And when you move this classifier in the down direction like this, okay, the data point which it exactly touches, the point where it exactly touches, that would be called as a support vector. Those are given special names called as support vectors. Okay. And that's the equation of line. This classifier is nothing but equation of line. Y is equal to mx plus b. Okay, that's the equation of line. And you simply come up with a formula wherein you say that anything which is greater than that line belong to one class. Anything which is below that line belong to another class. Simple. Okay. Now, how do we handle nonlinear spaces? One second. Sorry, just give me a minute. Even before this, there is one small thing which I have to explain. I don't intend to miss out on anything, so this is one small thing that I wish to quickly explain you guys. There's one small formula which, if I explain, I think the explanation will be complete. That's the reason. Yeah, I found it. Okay, so this part I wanted to explain. Let me go back. So here, this B is again called as bias, and this W is called as weight, similar to a neural net. Okay. All the data points. So we will also require that these hyperplanes, these two will give you nothing but hyperplanes. Equation of line. Okay, that is a line. But if you have more than one dimension, then remember I told there'll be this kind of a glass, but when you observe this glass from one side, it will appear as if it's a line. Okay, it would still appear as if it is a line. So this is nothing but a hyperplane also. Basically, that's the equation. It's a line. But if you have more than two dimensions, if you have a third dimension also, then we call it a hyperplane. The distance between two hyperplanes is given using 2 divided by W. W is the weights, all the weights put together. Okay, this gives you the distance. And this would give you Euclidean distance. To try to find the Euclidean distance between the points. Okay. So this gives you distance basically. The distance between these two hyperplanes here, between this hyperplane and this hyperplane, the distance should it be maximum or should it be minimum? What, friends? Should the distance be maximum or minimum? Maximum, absolutely. Since the distance should be maximum, if the distance should be maximum, what should happen to this weight, W? This is distance, 2 by W. If we want to get the maximum distance, what should this W be? Should it be maximum or minimum? Minimum, exactly, Vishan. If the denominator is minimum, distance will be maximum. So all you need to do is apply an optimization function, which will be to minimize this value, which is nothing but Euclidean distance. Euclidean distance means you'll have a square. You'll have a square. Okay. When you take a derivative of that, you get 2W. So if you want the 2 to be removed, you add 1 by 2. When you add 1 by 2, right, these two get cancelled, you get W. So your goal and objective is to minimize W, and that would actually maximize the distance, and that is exactly what we want. Okay, so these are the two formulae that I request you all to bear in mind. I think that's it. Subject to some constraint, but that should be fine. Okay. Here, until now we spoke about linear patterns. What if you have non-linear patterns? How will you handle it? One way of handling it is by introducing a term called as a slack term. Slack term means you give some penalty to the misclassified entries. Okay. And here we want to maximize the distance. When you want to maximize it, this vector means that arrow means vector. Vector means all the weights like B plus W1, X1 plus W2, X2 plus W3, X3, so on and so forth. We are talking about all those weights typically when you put an arrow. So vector is collection of all the weights. For this, we need to what? Minimize this weight. Minimize the weights. Plus, you also, for these misclassified entries, put a cost. Okay. The cost value is denoted using C. And you put a cost to all of these misclassified entries, and it is given a notation chi. This is given a special notice in G. Okay, so this is what we need to minimize. Now, it's the entire thing that we need to minimize, not just this. Even the incorrect mistakes also you need to minimize, and then the minimization algorithm kicks in. Or we have something called as kernel tricks, which are used to handle nonlinear boundaries. If you look at this image here, you have all the triangles and then you have the circles. Okay, you have the, triangles and then you have circles. Using a single line, you cannot segregate the triangles from circles. So the moment you apply something called as a kernel trick is nothing but some math operation. When you come up with, when you do some math operation, what will happen is these two dimensions would get changed and you'll get a new dimension altogether now, which is called as altitude. Okay, you get a new dimension. Earlier you had latitude and longitude. Now you have a different dimension called as altitude. Okay, and the data is completely changed. The underlying data pattern is completely changed. And now you can segregate these two classes using a single line. That is what kernel trick does. Kernel trick will take the underlying data, it will do some math operations and it will convert it into a different dimension. Here, you know that maybe altitude has been arrived at using latitude and longitude, but in real world, you will not come to know what is the new feature, what is the new dimension. You will not come to know. In the inputs that you have in your data set or the columns that you have in your data set would be called as features or dimensions. The new dimension is unknown, and hence, because it is unknown, your algorithm will become black box. Anything which is not known, anything for which you cannot have an explanation or interpretation would be called as a black box. And here are a few kernel tricks. One is called as a linear kernel, nothing much, just multiply the values. Polynomial kernel, we know degree is d, whole raised to the power 2, 3. If your data is like this, how to segregate the red crosses with probably the circles here, right? We need to use polynomial with 2 degrees. Then you have sigmoid kernel. You can also use tanh, obviously. When you have data like this, etc., we use sigmoid. Then we have Gaussian radial basis function. You have something called as radial basis function. That's the formula. Okay, so you apply those to ensure that when you have nonlinear boundaries, SVM starts working on that properly. Then we have multi-class classification problem. We know for a fact that SVM works very well when you have a 2-class classification problem. However, when we have a multi-class classification problem, how do we handle that? So we have one versus all. So what you do is, if you have 4 classes, you build one model by considering green as one class and all these 3 as the second class. Now it becomes a binary problem. Don't stop here. This is one model. Build another model, model 2, wherein you now start treating this as one class and all these as the second class. Then build a third module, wherein this becomes one class. All of these become the second class. Then build a fourth module, wherein this will be treated as one class. All of these will be treated as another class. Out of all these four models, whichever class has the maximum probability, choose that as output. Suppose here you have the maximum probability. Then you'll say that this is the class. That's the output. Okay, the output given the input should be blue class. This is how you handle the scenario. And then you also have 1 versus 1 scenario. You have 4 classes. Take 2 classes at a time. These two, these two, these two, these two, these two, these two, right? Take 2 classes at a time and build models. So if you have 4 different classes, you'll have to build 6 different models. And then go with the majority. Say this and this had highest probability. Okay, and majority are these two. So you go with majority. Say one model gives you green, one model gives you yellow, one model gives you this, and again this model gives you this. Then you know for a fact that out of all these models, majority are going with this. So that would be the ultimate output, the final output. So that's how you deal with multi-class classification problems. So SVM is a very simple algorithm. Not many people are using it today. Let me tell you. Why are we learning in that case? That might be a question, just to ensure that we have sufficient coverage. If someone asks you any question on SVM, you will be in a position to answer. That's it. So let me open this data set and show you first this data set. This is called as numbers data set, wherein, letters data set, wherein you have all the various alphabets. Given the alphabet, what will be on the x-axis, what will be on the y-axis, what is the width of the box going to be, height.
Hello, sir. Am I audible? Hello. Sir, am I audible? Hello.
Okay, sorry, friend. Again, same issue. So each time each time there is power cut, the generator gets switched on and then it's taking a while. Okay. So one of our friend had a question, right? Yeah, Vrishali, you had a question, I believe.
Hello. Sir, am I
Yeah, hi,
audible?
Vrishali. Yeah, you are audible, yes.
Sir, as we learn the neural network algorithms, all ANN, CNN, and RNN, then whether it is a good practice to go with the all shallow algorithm and after that apply the NN algorithm?
Shallow algorithm and then apply NN. Why? Why would you do that?
Because we
How do you
don't know that which algorithm gives us a better accuracy.
Okay, are you saying should we apply all these algorithms and then pick which algorithm gives good accuracy? Is that your question?
Yes, sir.
Yeah, obviously, yes. But then it's dependent on time, Vrishali. If the customer gives you, say, less time, say the customer says that I'm going to give you only 1 day time to complete the project. Maybe you can apply only 2 or 3 algorithms. Out of these three, you pick one, which is the best. If the customer would give you 1 month, obviously you'll have more time, maybe. So you'll apply more algorithms. So it is directly proportional to how much time you have at your disposal for experimentation. Point number one. Point number two is the moment you apply black box techniques, what are the disadvantages that you're going to foresee?
We don't know about.
There is not going to be any interpretation.
Yeah.
If a person applies for a loan and then you as a bank, if you have rejected the loan, what if this person gets back to you saying that give me the reason on why you have rejected the loan? If you say that I use some black box technique, so I don't know the reason, I just know the final result that you're going to default the loan, then this person might sue you, might put a case against your bank. So in these kind of scenarios, black box techniques will not be applied.
Okay.
You go with those techniques which give you interpretation and explanation like decision trees, maybe. Okay.
Yes, sir. Thank
So
you, sir.
depending on all these scenarios, you decide what are the bunch of algorithms which you want to experiment upon. Yeah. But to directly answer you, yes, you need to experiment with different algorithms and then you need to figure out which is the best algorithm. Absolutely. You need to do that. Okay. And here we have this letters data set. And given all the various inputs, we need to figure out which is the alphabet which is written. And when it comes to logistic kind of use cases wherein you might want to write the name of the person, etc. details, or you might want to get it printed and you stick it on the parcels. You want your algorithm to automatically recognize what those alphabets are. So this is the data set that we have. Given this data set, we will go to the SVM code and we'll try to run this. This is a very simple algorithm. And again, if you ask me, are people using it in the real world? My answer would be not really. Today, no. There were days when SVM was the most sought after algorithm, but today, at this time. Okay. So first of all, you load the required libraries, whatever you're aware of, load them. I'll do one thing. I'll not go after a new environment. Let me go to the base root environment. Yeah. Now let me launch Spider. Okay. So you have the libraries, then you have the data set. And then you load the data set. Okay. And then you do exploratory data analysis. You're using describe and you're storing it in an object called A. If I were to double click on that, you see that for all the numeric columns, you have the mean, standard deviation, minimum, max, and all these different percentile values. Okay, then you have support vector classifier. You're importing train test split, and you're taking this latest data set and you're splitting the data in such a way that you have 20% in test and you have another 80% in train. And once you have the training and test data, you're segregating the data, because when you run this algorithm, certain algorithms expect you to provide inputs and outputs separately. Hence, what you're doing is you're saying, let me go to the training data index location. Let me take all the rows and columns from 1 until n, and let me store it in training data. Then you're taking all the rows and just the first column, and you're calling it training Y. Then you have the test data, wherein you're taking all the rows and columns from 1 until n. And then you're taking only the first column, and then you're storing that in test 1. If you say help of SPC, you get to see a lot of parameters or hyperparameters. And you can obviously use that. And one of the things would be kernel. Okay. Kernel can take multiple values: linear, polynomial, RBF, sigmoid, so on and so forth. When it comes to polynomial, the default is 3-degree polynomial. Okay. Then you have various other, hyperparameters. You might want to go through these to understand more. Okay. Now, let me take linear kernel. That's the hyperparameter that we are taking. For all the other hyperparameters, the default values will be taken and you're storing it in this. And when you say dot fit of training inputs and output to build your model, then you're also saying that let me use my model and predict on the test data. Then you try to compare the predicted values with actual values. When the predicted and actual values are the same, you get true, if not false. On an average, how many times do you get true is something that you want to find out. 85% approximately. Here, if we were to change the kernel function to radial basis function, which most often than not will give you highest accuracy, most often than not. We are taking SVC and we are just changing the kernel function. These kernel tricks, linear means you're assuming that your underlying data is linearly separable. But what if your underlying data is non-linear? Then what do you do? So we say SVC of this, store. Then after building the model, when you say dot fit, you're able to fit the model. Then you're using the model and you're predicting on the test data. Then you get the predicted values. Now you're trying to compare the predicted values with actual values. Okay, and then you're taking the average. Wow, it's 92%. So that means from 84 or 85, there is 7 or 7.5% improvement in accuracy. Then you might also want to use your model and predict on the training data. Why do you need to do that? Because once you compare the training and test accuracy values, you get to know whether your model is a right fit or not. Yeah. Now, we run it. Look at that. 93. 0.93 or 93.8% accuracy. Here it is 92.5% accuracy. Both these accuracy values are high and close to each other. So you say that that's a right fit model. Otherwise, you play around with something called a tolerance level. And every time you have an algorithm go to help, try to look at what are the various hyperparameters and do something on that front. Okay. Now, while I talk, I'm getting a lot of thoughts on how to come up with a probably a block kind of a thing. Okay, anyways, that aside. There was another algorithm that we have already discussed, which was called as naive Bayes, right? And we could not run the code pertaining to that. So I'm downloading the data set and the Python code. Let me unzip that. And naive Bayes is a very good algorithm to be used when you have textual data to deal with. I'll go to the code, which has certain more lines to be processed, I believe. Yeah, that's okay. This is all text processing anyways. Each time you run a new code, make sure that you remove everything else from the memory so that the algorithm runs faster. And the underlying data set here contains textual data. In one column, you have data on whether each and every text message, simple message service, SMS, is a ham or a spam. Ham means it is not spam. And in the next column, you have the textual data. If you look at this, you have uppercase H here. Somewhere you might have lowercase o as well, right? So these two would be considered as two different words if you don't convert everything into a lowercase, maybe. The full stops, right? Numbers, the special characters, all of these things probably do not make sense. So you might want to remove those labels. And when you get this historical data, you manually label them. That's how any telecom company would have worked in the past. Manually read the message, label that as spam or not spam. Keep doing that, right? Manually, they would have done that. Now that we have access to algorithms, we will have to deal with it. First of all, the textual data as is, the unstructured data as is, cannot be supplied to your algorithms. Okay, you cannot supply the textual data as is to your algorithm. So you need to convert these this specific textual data into numbers. So we have various libraries, and then we import those. There is something called as feature extraction, wherein you have count vectorizer. So you want to convert your textual data into numbers, and then you want to fill those numbers with TF-IDF values. So yeah. Now let me copy this data and let me paste it. So you're saying pandas.read_CSV. You're taking the entire data set, and when you save it, you're using the encoding, which is ISO 8859, some format of it. And then using the assignment operator, you're assigning it to an object called email data, in which you have 5,559 rows and 2 columns. Now, what we are doing is we are also getting stop words, and you're creating an empty container of stop words first thing. Then you need to get this stop words data. Here we go. I'm going to copy the path, and I'm going to give the path here. R as attribute stands for read. So you want to open this in the read format as SW. SW.read means you want to read the content of this file and store it in stop words. Then here you have all of these words. You want to split wherever you have a new line. Wherever you have a new line, you want to split that into a different word. Yeah, you have all the different words. And also, whichever are not uppercase A to Z or lowercase a to Z, what do you want to do with those? You want to replace those with empty space. Okay, so you want to take each and every word, or each and every message, and you want to do that. After that, whatever is left out would be A to Z and A to Z only. Rest all you're removing it. And then you want to convert them into lowercase. This plus sign means even if you have continuous numbers, like these 0, 9, 0, 6, you want all of those to be replaced with a blank space. That is what you mean. Continuous series, replace it with one space. And then you're taking W, an empty container. You're saying for every word in this message, take every word and split it wherever you find a space. If the length of the word is more than 3, more than 3 means, so for example, here I have in, which has only 2. It's not greater than 3, so this will be removed. Only greater than 3 words would be taken and be appended to this W. And then all of those things you want to join. All the words. So for example, if I were to apply this specific user-defined function, okay, if you want to apply that user-defined function, let me put this, just in case it goes an error. Right? If I were to run on this cleaning text, right? Look at what happened. This is converted into a lowercase. This you are only 3 words, not more than 3. So these 2 are also removed. You don't have those. Having a is not greater than 3, so this also will be removed. Good, weak, full stop, because except for uppercase A to Z or lowercase a to Z, everything else you want to replace it with a blank space, so that would be gone. This is converted into a lowercase, so you have that. Checking in is not there because you want words with greater than 3 characters. Apply this function on the other text also, and you'll find the result. Here nothing is coming out because everything is less than 3 words. This is also one way of quickly cleaning the data. Now what you're doing is you're saying, let me go to this email data, let me go to the text, and let me apply this cleaning text on that. And then let me write it back to this. Look at that. All the cleansing has happened now. Okay. Then, wherever you have empty rows, say you want to remove those. Click on that. Yeah, all these are empty. like this. You got an empty, result when you applied your text screening on this, right? So you want to remove all of that. So what you're doing is go to email data, go to text, whichever is not equal to blank space, take only those rows and take all the corresponding columns and store it in email data. So 5,559, that count would obviously get reduced. Okay, approximately some 400 odd, no, I think 59, right? 57 odd were having blank spaces, they are removed. Now you import train test split and you split the email data wherein you have 80% training and 20% test. And then you are writing another function here. Split into words. So word for word in I split. So what you're doing is go to each and every row. Wherever you have a blank space, split every word in that. Right? This is a function that you are writing. And now you're saying, let me count vectorizer. How many times a word appeared? Let me count that. And analyzer would be first split everything into words. If you go to email data, for instance, you're saying go to email data text. Text is this. Then you're saying split each one into words and count the vectorizer and store it in something called as emails underscore bag of words. You cannot view it, but that's bag of words. So this is the function that you have defined. Now you're saying apply that function on the text data and get the all emails matrix. It's a sparse matrix. Sparse means you'll have a lot of zeros. Okay. Then you're saying, let me apply that on the training data. Let me apply this transformation on test data. This is what you have done. So you have the overall data matrix, test and train and test matrix, which contains bag of words, all the words and how many times each word appears. And maybe you might feel that TF-IDF transformation is something that I want to perform. TF-IDF transformer. Okay, you have just taken this. That means all the default values you want to take and you want to fit it on this all emails matrix, which is your bag of words. And you want to apply on the training bag of words and test bag of words also. And then if you look at the space, you have 4401 and 666, right? So let me tell you what happened here. Your overall data, you split that into training and test. In training, you have these many rows, and in test, you have these many rows. And you have two columns. One is the message, whether it is spam or not. Another is the text, actual text. Then what we have done is we have converted, we have taken bag of words. We applied that on the entire email data. Then we have applied this particular bag of words on training data and test data. Okay. When you applied on the training data, you got these bag of words. When you applied on the test data, you got the bag of words. Then what you're doing is you're taking these bag of words and you're saying, let me apply a TF-IDF transformation on that so that I get terms okay, and then for let me say rows, okay, documents, and then you have terms. So in training data, you have 4,001 actually documents. And when it comes to terms, you have 6,660 unique terms, term 1, term 2, term 3. Instead of bag of words, that is how many times a word has appeared, you are taking TF-IDF. So when you populate this table with numbers, you are getting term frequency, inverse document frequency details. Okay, and apply this transformation on test data also. Yeah, 11,001 and 666. Okay, then you have multinomial data. So you're going to scikit naive base, you're importing multinomial naive base as MB. You are ensuring that all the default hyperparameters are chosen. Then you're fitting the model on the training data inputs and output. Output is type, whether it is ham or spam. This one. Go to email train and then type. TF IDF has the inputs. Once you build the model, you use that model and predict on the test data. Oh, sorry. I didn't even see this. Is not defined. Which one is not defined? This one is it. Okay. So now you use your model and predict on the test data. Then you compare the test predicted values and actual values. You get a cross table. Now, if you look at this diagonal will contain the right predictions and this diagonal will contain incorrect predictions. And one interesting thing is there are no incorrect predictions wherein, there are 0 incorrect predictions. Originally, if you have spam were never classified as ham. But ham that is not spam, 46 of those were classified as spam. That means probably your model is lopsided. Right? So your model has learned very well the spam scenarios, but not spam scenarios, it did not learn well. Since it's lopsided, you have to once again play around with your regularization techniques. But then what I would say is you can apply the techniques such as overfitting, underfitting, etc. We are going to conduct a webinar on that. Means you'll probably have more representation of ham in your training data because that is getting misclassified as spam. Okay. Then you can also do this when you compare the predicted values with actual values. When you use double equal to, that means it's a comparison operator. If they're the same, you get true, otherwise false. How many times did you get true is something that you get to know when you look at mean. And the accuracy is 95%. You can also look at something called as accuracy score, which is a direct parameter. When you run it, directly it will tell you what is the accuracy. You can also now use your model and predict on the test data. You get the predicted values, compare the predicted values and actual values, get the accuracy, which is 97%, and then come up with a cross table. Here also it's the same. Spam cases are not classified as not spam. So that's a good thing in some sense. Okay. Next, you have something called as alpha. If you put alpha equal to 0, then no smoothing is applied. Okay. And the default alpha parameter is 1. And the smoothing process solves the emergence of 0 probability. Hey, what is this alpha value? Does it remind you of anything? Alpha value? Laplace parameter. We spoke about Laplace parameter, which is nothing but alpha here. Okay. Instead of letting the alpha value remain 1, you can change it. Let me change it to 0.75 and then fit your model. Whenever you fit means train on inputs and output, you take your model and predict on the test data. Then you get the predicted values. You try to compare the predicted values with actual values. Then you get the accuracy. Test accuracy. You can look at the measure, that is scikit-learn metrics. From that you import accuracy score. Accuracy score of predicted and actual values. When you run it, you get the accuracy score. Then you have crosstab. Crosstab is just to see whether your model is working well for one class, not working well for another class, etc. In this case, not spam going into spam means important emails you might miss out. Even if spam emails come into your inbox, you might select that and click as spam. But if important mails are going into spam, that's a challenge. So now you are building a model on the training data. Try to look at the accuracy. It is 0.97. You can also do a cross-check. Okay, only one entry is misclassified here. And here 95. Okay. So this is how you build your model, and this is how you make use of Laplace parameter. Keep changing your, try changing your Laplace parameter, which is nothing but alpha, and see which alpha value actually is giving you good result. But otherwise, also you can let the alpha value remain as is. Doesn't make a lot of, it doesn't make a lot of sense to change the Laplace parameter. Okay. So that marks the end of my course. What we are doing is we are coming up with a specific, branch of mind map, wherein you will quickly have all the machine learning algorithms, supervised or unsupervised, etc. And you will just have the details of all the hyperparameters, along with the default values. We won't give any explanation pertaining to that, but if you need explanation, there'll be a hyperlink. When you click on that, it will redirect you to blog to understand more about the explanations pertaining to the default values. Okay, that is what we are trying to convey. And you are expected to learn every algorithm, understand the hyperparameters pertaining to every algorithm, could be supervised or unsupervised. And then you also need to understand, out of these hyperparameters, what are your regularization techniques? And regularization techniques help you avoid or help you maintain bias variance trade-off. No, I will not cover hypothesis testing. The reason being, hypothesis testing is a self-paced e-learning. We don't have to spend time. However, Venkatesh, for my current evening batch, all these techniques I'm expected to cover, except for neural networks, because that would get covered as part of my AI batch, which I take, right? So there I will cover certainly, right? However, what I intend to do is, next week when we cover, obviously, we will get into confidence interval parts. Okay, then we will get into simple linear regression, multiple linear regression, logistic, lasso, etc. These I'm sensing that, okay, on Saturday we can cover, next Saturday. And Sunday, certainly for the first half, we are going to talk about multinomial, ordinal, and advanced regression. In advanced regression, you'll have Poisson, negative binomial, and some zero inflated Poisson, zero inflated negative binomial regression techniques. All right. After that, these will be on Sunday, kind of a master class. We will invite everyone else also to attend. These won't take more than 2 to 3 hours. After that, we will get into our survival analytics and forecasting. This is the roadmap. Okay. With that, I think many things would have completed. Then in the further master classes, obviously you'll have sessions on auto ML techniques and things of that kind, We will certainly notify you, and auto ML is also something that you people should be aware of. All right. So to become a successful data scientist, bare minimum, I'll tell you what is needed. SQL plus Python plus your data science plus Tableau. Bare minimum. If you feel that, hey, there are far too many things, I don't want all of those things, I want to quickly get a job. These are the things that you need to focus on. And live projects. Live projects, you have to consider those as a holy grail. This is what is going to shape you. And people, whoever have time, from tomorrow onwards, please attend 7:30 p.m. to 9:30 p.m. Get in touch with your point of contact, ask them to give you the access, because recorded videos of all the sessions won't be given to you. Because this evening thing, right, I'm ensuring that it is, these videos will replace your present full-length recorded videos. And hence, I would once again be traversing the complete thing, hypothesis testing and all of these. Once again, I'll cover so that it is available in the full-length recorded videos for everyone to access. That is the end objective. Okay, so I'll stop here, friends, because I have, let me stop.